So we've learned kinematics in one dimension, and we've learned the special case of free fall under the force of gravity. Now we're going to generalize a little bit to 2 or 3 dimensions, where gravity is still acting in the vertical direction, but you can have motion in the horizontal direction, okay, not just straight up and down. So if you remember, we did the free fall is the special case of acceleration being a constant due to gravity. And the way we would say that in 3 dimensions is the acceleration is minus g times the unit vector j. It has the value g, 9.8 meters per second squared, in the downward direction. There's no acceleration in the x or the z direction. Then the velocity for this special case of constant acceleration is whatever the initial x velocity is, plus, let me skip the y velocity for a moment, plus whatever the initial z velocity is. It's only the velocity in the up-down direction that changes, because only in the up-down direction is there acceleration. So that velocity is the initial y velocity minus gt, as we derived before. This equation, if you just look at the y component, is the thing we derived before. And in the x and z components, there is no change. It's constant because there's no force in those directions. Writing with vectors this way, sometimes it maybe looks complicated, but it's just like writing down 3 equations. The x velocity at any time t is equal to the initial x velocity. Okay, that's one equation. The z velocity at any time t is equal to whatever it initially was. Oh, look at that, v oz. It means v0 in the z direction. Okay, the z velocity will stay at that constant value because there's no acceleration in the z direction. And then the third equation is from the y component. Vy is equal to whatever it was initially, v0y, minus gt. So we write it like this with the unit vectors. We're really writing 3 equations, 1 for each dimension. When you get more used to the unit vectors, this is the convenient way to write it, because you write it all at once, but it really means 3 separate equations. Because the 3 vectors are orthogonal. This is really important. So they aren't in the same direction, so you're separating the problem into 3 separate problems, essentially. Okay, let me erase those 3 equations to give myself room to write down the position, but same idea. I can write an x position, a y position, and a z position. The displacement vector, r, is an x component, which is in the initial position plus the initial x velocity times t. So that's the x position times I hat, plus the y position times j hat, plus the z position times k hat. So let me do them each separately. The y position, if you remember from the previous lecture, is the initial y position plus v0yt minus 1/2 gt squared. Here's the term that comes from constant acceleration, and it's only in the y term because only gravity is acting, and that's only in the y direction. And then the z term is just z0 plus v0 in the z direction times t. Okay? Let me unpack this for you. This part of it is just like free fall. So whether I toss a marble up and it falls straight down in my hand, or I toss it over toward you but with the same vertical velocity, it would go up exactly as much and come down exactly as much. In other words, it would hit ground at the same time, but it would go farther in the horizontal direction. The thing I throw straight up doesn't have any horizontal component. Okay? Maybe the best way to think about it is the 2 motions essentially occur independently, even though it's the same object. Okay? If you threw it horizontally and there was no gravity, it would just go at a constant rate, and its position would be a linear function of time, right? V times the time. Now you turn on gravity, then it will accelerate in the vertical downward direction, and that motion will make it hit the ground sooner than it would if there were no gravity. But other than that, its horizontal motion is independent. let's see how much we understand about this conceptually, not just the equation. So I'm going to erase the equations and just talk about what it means when there are projectiles moving. Okay. We're going to think about a special case of two penguins sliding down an ice floe. So here is an icy hill. Somewhere below is the ocean of Antarctica, and the penguins start sliding down the hill, maybe starting from different points at the top of the hill. Okay. Penguin number 1 launches off this horizontal bit with a certain velocity. And penguin number 2, I guess it's not bad to tell you that penguin number 2 started higher on the hill, and later we'll learn why that helps the penguin go faster. But anyway, penguin number 2 launches at the same time in the same place, but moving twice as fast. Okay? And the question is, how does the horizontal velocity affect their trajectory? Does somebody want to take that? Katie.
Both penguins are going to spend the same amount of time in the air, but because the second penguin is going faster, it will travel a farther x direction than the one going slower.
Okay, great. So this penguin, you're saying, is going to start falling down and hit the water at the same time as the other one, which is going to go like this. This distance should be half the other distance. If blue penguin here is moving twice as fast, in a given time it should move twice as far horizontally. Now, why do they hit at the same time? Can someone explain that to me? Brian.
Well, as they're shooting off the ice floe, neither of them has a velocity in the vertical direction. So the acceleration due to gravity is going to cause them to fall at the same rate until they hit the water.
Right, exactly right. So they have 0 up-down velocity to start. So it's the equivalent. Their time they takes to fall in the water is the same as if you dropped a marble. At the same time they flew off the cliff, you drop a marble, all 3 will hit the water at the same time. Because it's just a matter of how high you are above here and the force of gravity acting with making constant acceleration. All right, let me see if I can ratchet up to a tougher one then. Suppose I have a ship on some water, and there's a cannon aboard the ship. So one cannonball goes pretty high and falls back down to hit this enemy boat. And another cannonball is fired more horizontally to hit this enemy boat. Okay? They are fired at the same time. That's what you know. They are fired simultaneously, and they follow these parabolic trajectories. Which enemy ship gets hit first? And why? Brian.
Does the green one get hit first?
I don't know. What do you guys think?
Yes.
Yes.
Why? Sean.
Because the blue one was shot up with more of trajectory going up, while the green one was shot more out, so there's more velocity in the y direction, while the blue has more velocity in the going up in the x direction.
Okay, but we don't know their initial velocities. I mean, we aren't told that they're the same or different or whatever. I think what you're saying is absolutely correct. We know their initial vertical velocities are different. That is, the initial vertical velocity of this one is much more because it goes higher than the initial vertical velocity of that one. But how do I know it comes down after this one? You sort of said it, but how could you persuade me, Katie?
Because they're traveling different vertical distances, which is what considers the time for it to reach the ship, and because it's a much less vertical distance for that one ship, it's going to get there a lot faster since it doesn't decelerate in the x direction at all.
Yeah, so another way of saying this is we could ignore the x dimension for a moment and just realize that the time it takes to get from the top here down to the bottom is the same time as dropping something from that height. And clearly dropping something from this height would make it take much longer to hit the water than dropping it from this height, right? So this guy takes twice as long as it takes to drop from this height because it's that time coming up plus the exact same time going down. They're symmetric as long as there's no air resistance. Whereas this guy also takes the same time to go up as it takes going down, but that has to be much longer because it goes higher. And dropping something from up here takes much longer than dropping something from here. So you guys did this really well, actually. A lot of people just think this thing must take longer because it's farther. And what I think we know from this is that being told the trajectories is the key thing. The height is the key thing that determines the amount of time it takes. Now there's some very practical problems we could try to do. Maybe we should do an example problem. Suppose we have a cannon firing a cannonball with some initial velocity, which has both an x component and a y component. And maybe we'll call this angle theta, the angle above the horizontal at which we aim the cannon. And I could ask you any number of questions, like how long does it take to land over here? And we'll have the ground be horizontal, because if the ground has hills, it's messy. I could ask you, at what angle would it reach the farthest away? I could ask you, if I tell you the time it takes to drop, tell me what the angle is. There are a whole bunch of questions that we could do here. Let me just give you a couple of sort of ideas to guide such questions, and then offline you can practice some problems with real conditions. The first thing to realize is as soon as you neglect air resistance, these trajectories are perfectly symmetric. This angle at which it lands will be the same angle, theta, as long as this ground is horizontal. And it will land with the same velocity going down, the same magnitude velocity going down as it was launched with going up here. So you can turn the problem around and launch a cannonball from here. It will follow the exact same trajectory, take exactly as long, and land on this cannonball there. What is that saying? Life and reality is not time reversible. We can't go back in time. But these particular laws of physics don't care about the direction of time. If I drop this cap to the floor and filmed it, it would look identical to a film run backward of someone throwing the cap up from the bottom with the same velocity with which it hit the floor, okay? So everything is time reversible in these kinematic equations. You can run the movie backward for this small amount of time. One other thing I want to say is, suppose someone asks you to calculate the time it takes for this ball to hit over here. For that, all you care about is the vertical motion, okay? Because the vertical motion tells you when you hit the ground, right? You're sending it up with some initial velocity. It's going to slow down, stop, and turn around and come back and hit. And it's that motion that defines the time when it hits here. Let me write that equation down. So the amount of time it takes, I start at a height y, which is equal to its initial height plus its y velocity times time minus 1/2 g time squared. Okay, this is our equation for the height at any function of time. Let me call this y equals 0, so this term can go away. I don't need it. I just starts at y equals 0. Okay, y equals 0 here. And I send it up with some velocity v0y, and it tootles around, and when this side is equal to 0, when y equals 0 again, that's when it hits here. Make sense? Okay. Can someone tell me what v0y is if I told you the magnitude of v0 and I told you the angle theta? Brian?
V naught times sine of theta.
Right, the magnitude of v naught times sine of theta. The x component is this and the y component is that, so this is a right triangle, and this height is the hypotenuse times sine of theta. The x, just for completeness, the x velocity is v0 cosine theta. Okay? So you have some initial velocity, which depends on what v0 is. I probably told you that, and I probably told you the angle or something, and then you could solve for when this thing hits y equals 0 again. At that time, then the question could be, how far did it go horizontally? And the distance it went horizontally is just the initial x velocity times the time plus whatever initial x value you want. And personally, I would just choose x equals 0 here as well, right? So you choose x equals 0. So where it lands, where it lands is v0 cosine theta, the x velocity, times the time that it lands, right? The time it lands is this, and this time it lands, you solve from there. So that's how you do these kinds of equations. And you can be asked many different problems. I think I just want you to understand the overall structure. Okay, if that's clear, we can go ahead and move on to relative motion. All right, relative velocity. Okay, let me start talking about relative velocity. So far, we have talked about motion with respect to some stationary frame. Like we're talking about the car driving down the highway, and we're thinking about the highway being stationary. Okay? And what's the motion of the car relative to the ground? But there are more complicated problems that are pretty important in daily life. If you want to take an airplane somewhere, the airplane will take off, and it has the capability of flying at a certain velocity with respect to the air through which it's moving. That's why when you fly to the West Coast, if there are heavy winds going against you, it takes an hour longer than if the winds are calm. Okay, because you are flying relative to the still air, essentially. The airplane defines your speed relative to the air. And if the air is moving against where you want to go, it slows you down. If the air is moving with where you want to go, it speeds you up. So concept of relative velocity is pretty important. Understanding, for example, if I tell you how fast an airplane can move with respect to the air, and I tell you which direction it's pointed and which direction the wind is pointed, you could tell me which direction the plane is actually flying. Or to turn it around, if I want to go from New York to San Francisco, or from Mumbai to Bangkok, that's a direction, and I need that to be the resultant direction of the plane after you consider the direction the wind is flowing. So these are calculations that airplanes and airplane captains have to do all the time. Okay, for our purposes, let's start with a slightly simpler example. Suppose we have a river, and I'm going to give you a top-down view of the river. So here's the river. There's water. That's my drawing of water. And you have a boat on one side of the river, and you want to get to the other side, let's say somewhere over there. You just want to cross the river, okay? So you aim your boat to go across the river. If there's no current, the boat will go in this direction, okay? That's where you're pointing, and that's where the boat is you're pushing the boat. But if there is a current, let's say in that direction, and let's call that velocity of the current, then the boat is going to be pushed this way even as you're driving it across the river. Okay? So the actual trajectory of the boat, if there's a current, is going to be more like that. You'll end up over here. And it's very simple to calculate the velocity of the boat with respect to the ground, okay, meaning the bank of the river, is equal to the velocity of the boat with respect to the water plus the velocity of the water with respect to the ground. So this is like a transitive vector equation. The velocity of the boat with respect to the ground, that's the thing we want to know. Where is the boat actually going with respect to the bank? We want to get from one bank to the other. Is a function of its velocity with boat with respect to the water, the still water, and then the velocity plus the velocity of the water with respect to the ground. Okay? So, for example, if I have this vector, this green vector is the velocity of the boat with respect to the water, and the blue vector, this blue vector is the velocity of the water with respect to the ground. And I want the sum of those two. So I take the vector sum. I have the boat vector here, v boat with respect to the water, and I add it to the velocity of the water with respect to the ground, and I get my resultant velocity, the velocity of the boat with respect to the ground. Tell me where do I point the boat if I want to go straight across the river? Okay, let me leave the current where it is, and I want to now send the boat directly across. I would like to land right here. This is what I want the trajectory to be. Where do I point the boat? Brian?
You would point it in a direction so that the component that's parallel with the river is equal and opposite of the current of the water.
Good. So I'm going to point it upriver some direction such that this component of it is equal in magnitude to that current, so that they cancel, so that this motion cancels, and then it has to cross the river with this component of the motion. Is that going to take me longer than if there's no current, or less time? Is the current helping or hurting? Yeah. Assuming I'm operating the boat at the highest speed possible, if there's no current, then it just puts all of its speed across, going directly across, and it goes quickly. But if it has to fight the current, then it only has a smaller component of its speed actually going across the water. So it takes longer. Okay. Questions about this? You guys seem to have picked this up. I think we should go offline for a good example problem. Make sure this is socked in, but okay, I think we're good on that. So I think I will go ahead and add the uniform circular motion here, since Katie enjoys it so much, and we're not going to do the fun parts yet. We'll get to that later. Okay, so that's what we learned about relative motion. You can practice some problems yourself, but for a typical problem might be that I'm aiming an airplane 45 degrees west of north, and the wind is blowing at some other degree with some other velocity, and where is the plane actually going to go? That would be a typical problem that you could be asked to do. Okay, so let's move on to the idea of uniform circular motion. This is kind of relevant to this module because it's two-dimensional motion that we're talking about. But conceptually, it's a bit different. Moving in a circle is code for I know what the acceleration is. So in free fall, we know what the acceleration is. It's the acceleration due to gravity, or g. We know what it is. Here's another case where you know what the acceleration is. So let's draw a circle. Think of it as a horizontal circle. There's no gravity in this problem, so there's no up-down in the circle I'm drawing. It has some radius r. And let's say we're going counterclockwise around the circle, so there's some object traveling counterclockwise. When someone tells you an object is moving in a circle, you know immediately this thing I'm about to tell you, which is that it has an acceleration, which is called centripetal acceleration, equal to the velocity squared over the radius. Another way of saying this is if that's not its acceleration, it's not moving in a circle. So someone telling you an object's moving in a circle is code for that's its centripetal acceleration. Let me give you a sort of practical sense of what that is. If you take any object on a string and you whirl it around by hand, okay, imagine that you want to make it go around faster. You have to pull harder on the string that you're whirling it with, right? Can you feel that? You've all done that. So that increased force is needed. If you increase the velocity, you need an increased acceleration toward the center in order for it to stay going in a circle. So this is a very useful thing if you're trying to analyze, for example, there's a great, I have a great example. I don't do this, I have to admit to you. When I go to the fair, I get on the merry-go-round on an ambitious day. Never get on the Ferris wheel, those horrible scramblers, the roller coaster. No, it is not me. But there's a thing you can do, which actually I believe I have done, but only once, and I would never do it again. You go into the sort of circle of death. You're against the wall, and when they start the thing, it starts spinning, right? And once it gets to a certain speed, they drop the floor away. And you no longer need the floor because you're pinned against the wall, right? So that's a fun thing. Let's analyze why that is. Well, we'll have to leave some of it for later, okay? Because we have to get to the Newton's second law in order to do this problem properly, but we'll remember to come back and do it then. But the point is that as it speeds up going around, the wall pushes harder and harder against you as you speed up. The faster you go, the harder the wall needs to push you in order to keep you going in a circle. And you're not going to not go in a circle because you're not going to fly through the steel wall, right? That's not going to happen. So the wall is pushing you harder. And as it pushes you harder, you start to be pinned against the wall. That is, gravity is pulling on you, but there's a friction force holding you to the wall. So it keeps you from sliding down. And believe me, if they slowed that thing down without bringing up the floor, you would slide down. I mean, right this minute, if I lean against the wall, and I'm not going to do it, but if I move my feet out, I would just fall down. I can't push against this wall hard enough to not fall. If I don't stick to the wall when I push against it. But if I were able to push harder, and that's what happens in this game, you move around quickly enough that it's pushing really hard against you, and that therefore friction keeps you upright. We'll come back to this problem when we learn to do problems with force and motion. But the key thing I want you to understand now is that if you're told an object is moving in a circle, whether it's a race car around a bank track, or you on a whirly thingy, or a bucket of water being swung overhead, right? If I held a bucket of water upside down right now over my head, I would get very wet. But if I fill it with water, I can swing it around in a way that it doesn't get me wet. And the reason for that is because it's falling at the same rate as the bucket is moving down, basically. So circular motion is telling you something about what the acceleration is inward at every point around the circle. Okay, that concludes our 2- and 3-dimensional simple motion. We've kind of talked about forces a little bit. Just now I'm talking about the force of the wall on me. Before we talked about the force of gravity. Going forward, we're going to take these tools we have of vectors and motion, and we're going to put them together and study how forces directly cause acceleration and motion, and how they're related and how we can do it. Okay, so next module, we'll do that.